Hello, my name is Quincy Bryant. My other REU partner is Olumide Sarumi, and our RET teacher is Cody Smith. And the name of our project is Implementations of Distributed Control Algorithms for Multi-Vehicle Systems. Our project goals were to learn fundamental concepts of control systems, how to implement control algorithms on target devices, to gain experimental skills involving programming and control of ground vehicles, learn the concept of string stability and cooperative ACC of a multi-vehicle system, and ACC basically stands for Adaptive Cruise Control, and finally, to be exposed to programming and simulation in MATLAB and SIMULINK. So we were introduced to many topics, and one of those topics were MATLAB, and MATLAB is basically a programming platform for engineers, and SIMULINK is a graphical programming environment for modeling, simulating, and analyzing multi-domain dynamical systems. And throughout the weeks, we were able to use MATLAB and SIMULINK effectively to help us understand control algorithms. We were also introduced to Arduino control systems, PID controllers, string stability, and speed code. Arduino Do is a microcontroller board that measures the necessary sensor data and then sends that data to the PC for SIMULINK to compute. And as you can see in the bottom right, this figure is basically the implementation of work between SIMULINK and Arduino Do. PID stands for proportional, integral, and derivative. The PID controller is one form of a feedback controller, which is the simplest controller there is. You have the integral branch of the controller, which removes the steady state error, the derivative branch of the controller, and this branch increases the performance of the system and keeps the system from overshooting. And lastly, the proportional and the integral branches both work together to lower the error down to 0.
Okay, so here we have the dynamics of the two-wheel differential mobile robot. On the right, we have the control law that is designed. And this is the geometric representation of a two-wheel differential mobile robot. On the left, we have the dynamic equation. This is basically a differential order math equation where Q is the generalized body velocity, U is a vector of the wheel's torques, Z is a task space position vector, and X is defined as the state vector. The kinematic, so here at the bottom, we have the kinematic and dynamical parameters, which are given by. Okay, so this is the implementation with SIMULINK. By first glance, you could probably see the Arduinos and the PID controllers. And this was previously explained by my partner, Quincy Bryant. And this is where I mesh in and tie in everything together to help with your understanding. If you never used MATLAB or SIMULINK, you're probably wondering, where are these shapes? Where are these blocks? What is this graph showing me? And that's okay. That's okay. I'm here to help with your understanding. The blocks represent math equations and modeling components. On the left, we have the set blocks that come with Arduino Do inside SIMULINK. All the way to the right, that box right there is our robot. Next to our robot, to the left, we have our PID controllers. On top and the bottom of our PID controllers, we have our scopes. And our scopes just read us our output. The challenges with this was really with the Arduinos because the preset pins to the Arduinos were 8, and the output we were getting was not what we wanted. But the funny thing with this is Taiwo just set one of the pins to 9, and it just came up with our output, and that was pretty funny to me. So the SIMULINK implementation with PID controller. So like I explained in my last slide with the math equation, this is where the math equation comes into play. During this research and just learning about controllers and multi-vehicle systems, dealing with controllers in multi-vehicle systems, the basics start with math and knowing differential equations. So the core base starts with math and differential equations. That's important. Differential equations are very important. So this is where the math equation from the previous slide ties in. It plays its part, and as you can see with the blocks, that's the math equation with the blocks. And basically what that is doing is starting to rotate the tires on our two-wheel mobile robot. And to the right of that, we have the velocity wheel. We have the velocity of the wheel. This is the scope, and this is the output shown, basically showing us that velocity is controlled and stable. Okay, so here we have our results. On the top left, we have our actual path traveled by our two-wheel robot, and on the right, we have our desired path. And this basically just shows that the path tracking is controlled and stable. Between these two plots, they are very similar, just very similar. Just we have a little error right there from the desired path, but nonetheless, at the bottom we have the control law input from the dynamics page, and to the right of that we have this scope that shows the velocity of the robot from the control input given.
Right, so some high school activities that I've found while working on this project, one of which would be a short lesson on what control systems and PID controllers are, for instance. I'd be using the cruise control that we see in cars as the primary contextual example for the kids, because that's probably going to be one of the most applicable or one of the most relatable examples that they might have in their lives for what control systems that they use. To help them understand it and understand what they do, we could show these graphical examples. Say, okay, your car wants to go at 70 miles an hour. So this blue line would jump straight up to 70 on the y-axis and would stay there for the whole time. And these black, green, and red lines would be different iterations of the control system working through its calibration per se, hovering around that number until it finally evens out at it, or in the most beneficial example, the red line here, just going straight up to it and asymptoting off at it, which is what control systems do. So we could talk a little bit about what they do. I'd be hesitant talking about how they work, though, because from what I've learned about control systems, which I learned all about them in here, having only a physics degree, we didn't really talk about control systems a whole lot in my physics program. So in what I've learned so far about them, most of them just use a bunch of differential equations. And high school students don't use differential equations unless they're taking super advanced like college level classes. Like even in Calc BC, they're only ever asked maybe to write a differential equation and not solve it. And seeing as how, especially personally speaking myself anyway, I don't teach any of the calculus-based physics classes at my high school. So talking about the hows of how these things work wouldn't necessarily be too beneficial for me. It would be over a lot of the scope of what I'm supposed to be doing. Maybe if you teach the APC classes, the APC or AP Physics C classes, might be more applicable there. But even then, I'd say I doubt it, because even then you're still only being asked write the differential equation, don't solve it. Next idea. So our control systems here are working with robots, right? And all these robots are moving in some way. So if your school, like mine, has a drone piloting program, you could go through and do some pretty basic kinematics work with the 4 different thrusters of a quadcopter drone. So you can work out the free body diagram of it, say, okay, they each provide the same amount of thrust maybe. What angle of the drone would you be looking for to provide this speed for the control system to aim for? In our case, we were hoping to work with 2-wheeled robots. That's probably going to be more applicable for a lot of classes because they're a lot cheaper to get a hold of. So you could work with the differential rotational kinematics between the 2 wheels of the robot, working with the different rotational velocities coming together to make a single, translational or rotational velocity for the vehicle if it's rotating or if it's just going in a straight line. And you could use that to write, if you don't have the materials around there's plenty of grants available out there for you to write and pretty easily get your hands on these 2-wheeled robots and some Arduinos. Have the kids build them, put them together, have them do the coding. Maybe some of it could be applicable, but for the most part, you'd probably just be looking for some of these papers that have these algorithms already out there for you. You can upload them in the Arduinos. Once the kids have, shown you their kinematics work is, up to snuff, and then let them work together and have a nice little fun demo of, 10 or so of these robots working in conjunction after the kids doing the math to get them to work out, right? So that's what I have for classroom applications here. The last thing we want to talk about for our project are future works for this research. The first of which here, we want to explore different analysis methods for the string stability. We only researched one, or we only went over one of them from a specific paper in our research today. And there are plenty of other methods out there for us to go over. So given more time, we could implement different methods to see, okay, does this stability match up under these other methods of analysis? And then the other two just come down to the virtual nature of our research this summer. We couldn't get our hands on the SpeedGoat real-time simulation or any actual two-wheeled robots because they were all in the lab, and we had troubles remoting in to the lab at FAMU to get access to the SpeedGoat hardware. So both of these are definitely things that, given another setting or more time to work on, we would love to try to implement given the work we've already done on MATLAB and SIMULINK. And from there, I think we're opening up to questions. Thanks for your time.